Okay, hello everyone. Let's get started where we left off last time. The example that we started looking at was this base excitation. So what we have is a single mass that is attached to a spring, and so the movement of the base is the input, and we are interested in the output of the system, which is the displacement of the mass. So there are two state variables forming the state vector. The input, for convenience, instead of simply being displacement of the base, it is stiffness of the mass times displacement of the base divided by the mass itself. And that makes the model more convenient to write. So our objective is to look at, of course, the open loop system, see what the expected behavior would be based on the location of the eigenvalues, and then go and apply the two control techniques that we have covered so far, the output control versus the state feedback control, and put them in perspective. Compare them to each other to see what they offer in terms of the spectrum of behavior that can be expected from the closed loop system. So the first step that we took was we started from the free body diagram of the system. You can see it right here. We wrote the differential equation and simplified the differential equation. So we got to this second order differential equation where x of b is the displacement of the base. Then we went ahead and simplified this further. So we got to this form, x double dot plus k over m is equal to k over m times x of b. That is why we call this the input, to make it simpler. There is no set input. This is just a matter of convenience. State vector is made of x and x dot. Y is the output. So the next step we took was to write the four matrices of the state space model. The typical first row of A matrix for this system, that is a second order differential equation, is 0, 1, 0 here because that equation simply is x dot is equal to second member of x. Therefore, this is also 0. And when you look at the differential equation, this is minus k. If you take x term to the other side, you will have minus k over m times x. Nothing is times x dot, that's why it is 0. And 1 is multiplied by k over m times xb, which is our input. So the second row of the state space model is this differential equation, the second order differential equation. And this portion of the state space model simply identifies which of the two state variables is our output. In this case, the first one is our output, which is the displacement. The next step we took, still in the open loop system, we haven't done any control, was to look at the eigenvalues of A. So we set this determinant, lambda I minus A, and set it equal to 0. So if you find that determinant of lambda I minus A and set it equal to 0, you get to this second order polynomial. There are two values of lambda that will make this equal to 0, and those two values are plus minus square root of k over m. Now, realizing that stiffness and mass will always be positive numbers, so we don't have a negative stiffness or we don't have a negative mass, at least in this world that we know. So what is under square root is definitely a negative number. So what we do then is factor out negative 1, square root of negative 1 as j, and then it becomes plus minus j square root of k over m. So what does this tell us? It tells us that the open loop system has two imaginary eigenvalues, which is associated with a response that is purely oscillatory. So if you, going back to the physical system, if you give a unit step input, so if you push this base up by 1 unit, what will happen to the mass is continuous oscillation that continues forever. So it doesn't decay In other words, the damping ratio is equal to 0. The angle, look at the angle that each of these two eigenvalues make with the imaginary axis. That angle is 0. What angle are we talking about? This angle. When you connect the origin to one of the two poles, that will be a line. So that line with the imaginary axis has an angle of 0. Therefore, sine of that angle is 0. Therefore, damping ratio is equal to 0. So let's start by writing that zeta for open loop is 0, and omega n, natural frequency, which is the distance to the origin, is the square root of k over m. So this is what we have. So this, in other words, this is an undamped system. Could you take a look at this lab and see if anybody's waiting there and let them know that we're meeting here? Thank you. Okay, so our objective, next objective, is to design an output feedback controller. And the way to assess how the controller performs is to look at the eigenvalues of the closed loop. So what we are going to do next is to create a closed loop system, which means you're going to take the system, feedback the output only through a negative sign, compare it with R, and this error signal enters a constant value k, which then creates our input. So this is error, this is output controller. So this is an output control system. Now, as you recall, the methodology for designing an output feedback controller is to form a closed loop, which is going to be A minus K times B times C. So for an output feedback controller, A of closed loop is A times K control gain times B times C. We are going to face some difficulty here. And the reason is we have a K for stiffness and a K for controller gain. So let's distinguish them by calling this Kp. So I'm going to call this Kp times B times C, and Kp stands for a proportional controller. So it's a controller gain that is proportional. So the controller gives an output that is proportional to the level of input. So, so we do it as Kp. So let's go ahead. So A was 0, 1, minus K over M 0, minus Kp. B was 0, 1, and C was 1, 0. So this becomes 0, 0, 1, 0. And since it's multiplied by Kp, this simply becomes Kp with a negative sign. So a closed loop is going to be 0 minus 0, 0, 1 minus 0, 1, minus K over M, minus Kp, and 0. If you set lambda I minus a closed loop, that is going to be lambda minus 1 K over M plus Kp lambda. We have to set this equal to 0, and in doing that you'll get lambda squared plus k over m plus kp equals 0, which gives you the following two eigenvalues for the closed loop. So it's going to be minus square root of k over m plus kp. Now realizing that I just made a mistake, that the negative is under square root. So realizing that the negative is under square root and k, m, and kp are all positive numbers, I'm going to take a middle step, drop the middle step and write it as k over m plus kp. Okay, so what are these two? What are these two values? Let me give you a few seconds to get up. What are these two values? They are eigenvalues, but eigenvalues of what? They're eigenvalues of? Yes, the closed loop system that is output feedback. Okay, so we established that. Now, what does it mean? In other words, what can the output feedback controller do for us? To what extent can it affect the behavior of the system? In order to assess that, we need to draw a root locus to see how the two eigenvalues are displaced as we increase the controller gain kp from 0 to larger numbers. So let's go ahead and make a quick table here. So kp here, lambda 1, and 2 here. So if kp is 0, where are the two lambdas? They're located as plus minus j square root of k over m, which are the exact same eigenvalues as the open loop system. So if kp is 0, we are dealing with the open loop system. And that is expected. Now, as kp increases, what happens? How the two eigenvalues are displaced? They will move further away from the origin on what line? On the exact same line, imaginary axis. So they move, so as k goes up, imaginary or moves away, or they move away from origin on imaginary axis. So if you draw the root locus, originally the two eigenvalues are located here and here, and as the controller gain increases, they keep moving up and down. So this is minus j square root of k over m. This is plus j square root of k over. Which means what? Which means as controller k increases, what are we affecting? The only thing that we are affecting is natural frequency of the system. Are we changing the damping ratio at all? No, the damping ratio remains 0. So as we increase k, damping ratio doesn't change. So as kp goes up, omega n goes up, zeta remains equal to 0. So that's the limitation. So the limitation of output feedback for us. It can make the system faster by changing its natural frequency, but no effect on the damping ratio. So let's now switch gears and go to state feedback control. So the next thing we are going to do is to look at state feedback. Which means in this case we are feeding back the state vector as opposed to output only, which will result in a new A closed loop, which is A minus B times K, where K is a vector. It's a column vector. I'm sorry, it's a row vector of dimension 2. So let's go ahead and repeat what we did. So A again is 0, 1 minus k over m 0 minus b was 0, 1 and k is k1, k2, where k1 is the gain that is multiplied by x1 displacement and k2 is the gain that is multiplied by the velocity. So let's write that down once to make it clear. So k1 gain of displacement and k2 is gain of velocity. So in making the input to the system, we are going to feed back displacement multiplied by k1, feedback velocity multiplied by k2, and these two with a negative sign will be added to kr times r. So what did we say? So we said r comes in, gets multiplied by pre-filter kr. This comes in with a positive sign. From here, with a negative sign, we have k2 that gets multiplied by x dot. We have another line with k1, which is multiplied by x. These two are the two state variable of the system, where y goes out. So the difference, so all of these come together and become the input to the system. So the result of these three, so in other words, the input to the system is kr times r minus k1 times x1 minus k2 times x2, where x1 is displacement, x2 is velocity. Okay, so let's see how difference the performance of this controller will be. Okay, so let's find a closed loop. It's still a 2 by 2 matrix. So I'm going to multiply these two and then subtract at the same time. So if you look at row 1, 0 gets multiplied by both K1 and K2. So row 1 is 0, 0, and row 2 is K1, K2. So let me write it down. So this is our A minus K over M 0. So if you multiply B with K, row 1 gets equal to 0, 0, and row 2 becomes K1 and K2. So if we make the subtraction, 0 remains 0. This is 1. So this becomes minus K over M minus K1, and this becomes minus K2. So the difference should be even obvious at this stage. So if you look at a closed loop of the previous case, here in this a closed loop we had 0. So we didn't have any effect on here. But if you look at the new a closed loop that we have a K2 here, which is going to have some effect. So let's go ahead and calculate the eigenvalues of this matrix. So lambda I is going to be lambda here, minus 1 here, K over M plus K1, and lambda plus K2. So finding the determinant will give you lambda squared plus K2 times lambda plus K over M plus K1 equals 0. Of course, we can try to find the roots of this equation, but equally effective is if you go ahead and write the characteristic equation of a standard second order system. So lambda squared plus 2 zeta omega n lambda plus omega n squared equals 0. Still we have two eigenvalues, but now we have more degree of freedom. We can do more. How? As you can see that as K1 increases, what is it going to affect? What is the effect of K1? Look at the equation. On natural frequency. So as K1 goes up, omega n increases. On the other hand, as K2 goes up, what is increasing? K2 basically increases zeta omega n. So K2 is simultaneously affecting zeta and omega n, but between the two, by adjusting values of K1 and K2, you can create the damping ratio that you want and the natural frequency you want. So in other words, the open loop system has no damping. Physically there is nothing in the system that dissipates energy. But here, with a controller, you're effectively adding damping. It's a virtual damping, but the effect is like a physical damping. So you can solve many different cases. For example, what K1 and K2 you should choose so that your natural frequency is twice the original natural frequency. So it's twice square root of K over M. And your damping ratio is 0.7. What K1 and K2 will give you that? So if you compare these two characteristic equations, you can see that omega n squared is equal to k over m plus k1, equating the coefficient of power 0 of lambda, and k2 is equal to 2 zeta omega n. So if you substitute for the desired omega n that you want in the first equation, this becomes 4 k over m, and here it becomes 2 times 0.7 times square root of k over m. So 2 times 0.7 is 2.8 square root of k over m. So we have k2, and the next step is to calculate k1. So k1 from that equation, if you take k over m to the other side, k1 becomes equal to 3 k over m, and k2 is 2.8 square root of k over m. So by choosing k1 and k2 this way, you can effectively create a system that is underdamped. Now, think about it. What are we doing, physically speaking? What is this controller doing? So we designed the controller and set a set of gains. But effectively, what the controller does is it affects the input to the system. So the way we move the base of this system, the way we move the base effectively creates damping. So imagine you have a mass attached to a spring on your palm. So if you jerk your hand, this will start oscillating. But you can move your hand in a way that the whole thing moves up, sometimes without any oscillation whatsoever. Can't you do that? That is exactly what the controller does. So how do you do it? You feel how much this is moving, and you react accordingly. And that is exactly what is happening here. In order for this full state feedback controller to work, you need two sensors. You need to monitor how much the mass moves, and you need to monitor how fast the mass moves. With these two pieces of information combined, you can make any behavior you want out of this system. Any questions before we move forward? Okay, so let's review and summarize everything that we have studied so far about this full state feedback controller. So this is the block diagram. I know we have shown it in different ways, but essentially the block diagram of a state feedback controller, or sometimes called, as you hear me interchangeably using them, full state feedback control, or just simply state feedback control. We are feeding back x, multiplying it by a gain vector of negative k, and this combined with RKR incorporates the controlled input to the system. Of course, there is disturbance. We have mentioned that before. Of course, there would be different input that enters the system that is out of our control. And one of the expected properties of a controller is to reject that effect. Even though we have input that enters the system that we have no calculation, no control over, our controller should be able to compensate for that. So that's the expected behavior of the controller as well. So in other words, the input to the system, as we know, is minus k times x plus kr times r. And this is the closed loop A matrix, as we already discussed. And the way to choose the controller gains is to put the eigenvalues of the closed loop system somewhere that is desirable for us. We can also, with the controller, calculate the equilibrium or steady state value of x. We have already done that. We can calculate the equilibrium or steady state value of y rather, and we can find, as we have done already, this is just a summary, we can find value of kr to give us zero steady state error, which means in steady state error, y is equal to r, which is the desired performance of the system. Now, I here painted a very rosy picture. And with everything this good, there is always a catch. So what is the catch here? So I showed you that if a system is controllable, let me remind you of that fact. If a system is controllable, you can basically achieve any behavior you want out of a system. So you can make a system that is undamped and underdamped, or even critically damped, or overdamped, whatever you want with a system. But what is the catch? What is the payment here? What do you have to pay to make it happen? The requirement for a full state feedback controller is full state feedback, which means for every member of a state vector, you have to have a sensor. That's how you measure variables. They don't just come to us. We have to have a way of measuring. So the cost associated with implementing a full state feedback controller are those extra sensors that we have to buy. Now, let's say we are talking about a fourth order system. A fourth order system means the state vector is made of 4 variables. If we were doing output feedback only, we would buy only one sensor. We will only measure one of these state variables. But if we are trying to do a full state feedback controller, we buy an additional 3 sensors. So the cost is multiplied by 4 essentially here. So that's the cost. Now, sometimes you can say, okay, I can afford it. Our sensors are not as expensive, so I will go with full state feedback control. Now, the challenge is sometimes even you're willing to pay, it is sometimes very difficult or sometimes impossible to make measurements. Imagine a steel mill. So you are continuously melting iron. And let's imagine you're controlling this melting operation. So you want to achieve a certain throughput, you want a certain quality in the iron. So all of that is controlled by controlling your furnace that does the melting. Now this furnace reaches a quite high temperature. And in order for you to have full control on the furnace, you need to have multiple measurements of the melt itself, what you're melting continuously. Do you think it is possible to make measurements of molten metal continuously? It is not impossible, but maintaining a sensor system that continuously measures at various locations of this could be quite challenging. So the question is, can we do something else other than measuring all the state variables? So we still want to have a full state feedback control, but we don't want to pay for the price of all the measurements and maintaining all those sensors. Is there another way? That's the question. Before answering that question, I want to show you an alternative way of a block diagram. Now look at this block diagram. What do you see? You see an input U multiplied by a matrix B. Okay? And so this is B times U. Here what you have is matrix A multiplied by what? What is the content of this line? What is this? X multiplied by A, and this is B times U. So the content of this line here, right here, is A X dot plus B U. What is this equal to? I'm sorry, it is not AX dot, it is AX. This is X, so AX plus BU. So AX plus BU. What is it equal to according to the state space model? AX plus BU is equal to? Isn't it X dot? Isn't it the first part of the state space model? Okay, so if you take BU and add to it AX, you have X dot. Now if you integrate X dot, which in block diagram language can be shown with multiple ways, including 1 over S. 1 over S, effect of 1 over S is integration. So if you integrate X dot, what do you arrive at? If you integrate X dot, you get to? What is integral of X dot? What is this equal to? X. It's equal to X. So integral of X dot is equal to X. So that's exactly what this block diagram is telling. The story this block diagram is telling is that you take U multiplied by B, you take X multiplied by A, this will give you X dot. If you integrate that, you get to X, which you needed to multiply by A to create X dot. And X multiplied by C if D is equal to 0. So if D is equal to 0, Y is equal to C times X. So you take this multiplied by C, you have the output of the system. Now, full state feedback in absence of the pre-filter means take X multiplied by K, bring it with a negative sign, and that's your, when you compare it to R, that's your input. So in other words, this is the block diagram of a full state feedback controller. And there is a reason we are showing it this way, because I'm going to use this block diagram to answer the question that I just posed. The question was, I still want to do full state feedback control, but I don't want to pay for measuring X. I want to be cheap and simply and only measure Y. Can I only measure Y and still do full state feedback control? That's the question. So let me write it down. Can we only measure Y, but still have full state feedback control? Which requires, by the way, having access to X. So in other words, I'm asking you, can I measure Y but have access to X? And we are going to try to answer this question using this example. What is this example? This example is a magnetic levitation system. So you're basically using magnetic force to suspend a mass. The application, like a magnetic railroad. So you suspend your cart instead of a wheel, basically, with friction and all the losses traveling on a rail. Another application, a suspension. So you want to keep something suspended, so you have you could have very precise control over its motion. So what are the state variables? One of the state variables definitely is the current that passes through the magnetic circuit. So this is V. It causes a current to pass through the circuit. That's one of the state variables. You can write the equation for this. The equation is V is equal to Ri plus L di over dt. So that's one differential equation. And this coil here, with this inductance, creates a magnetic force on this mass. So the mass will fall down in the absence of a magnetic levitation that brings it to the center. So because this is a mechanical system, the movement of this mass is measured with this variable h. So when h is 0, we have a perfect operation. So the mass is in the middle of the coil. It's where we want this to be. So h is the displacement of the mass, and h dot is its velocity. So these are the two other state variables. So we have three state variables: movement of the mass, velocity of the mass, and the current that passes through the circuit. And this, by the way, is going to be a nonlinear set of differential equations. But for now, let's not focus on how we get to the model. Let's assume we've done the modeling with a set of variables for R, a set of parameters for R, L, and M. You have these three matrices. So you have matrix A, you have matrix B, and you have matrix C. Let's go ahead and bring MATLAB up and see how this system behaves. So I'm going to define A. So A is going to be equal to 0, 1, 0. This is from the mechanical system. The second row is 980, 0, minus 2.8. And the last row is 0, 0, minus 100. So this is the A matrix. The B matrix is going to be equal to 0, 0, 100. And the C matrix is 1, 0, 0. By choosing C matrix as 1, 0, 0, basically we are saying the output of the system is the displacement. The output of the system is the displacement. And D, by the way, is 0. So we are going to define our system as state space of A, B, C, and D. So this is our model. So the first thing we are going to do is we are going to look at eigenvalues of A. So what do you see? What are the eigenvalues? They're all real, which means what? Which means when the eigenvalues are real, what does it mean, basically? The quickest things that come to your mind is this system doesn't oscillate. There is no imaginary part, which means immediately no oscillation. So it seems like a good news. Until you look very closely and you see, what do you see that is bothering you here? There is an eigenvalue that is positive. There is an eigenvalue that is positive, which means what? Which means this system is unstable. What does it mean physically?
If you give it an input, the output will...
Which means what? Look at the physical system. Input is the voltage. Input is the voltage. Output is what? We said output was? Output was? Look at the C matrix. And look at the state vector. What is the output?
The height of
The displacement of the mass from the center of this coil. That's the output, right? So let's go back. You give this a constant input. There is an eigenvalue that is real and positive, which means what? The output grows without bound, which means what? Which means this falls. The mass doesn't stay in the coil. It just falls. Doesn't matter how much, as long as it just leaves that coil, we don't care. This system is not going to work for us. So this system, the open loop system is unstable, which means if you just give it 1 volt, it's not going to just look at the fact that there is 1 volt and stay there. Even if you give it 2 volts, 100 volts, whatever constant voltage you give it, either it will fall or it will be just shut up. So it will not stay where you want it to stay. That's the bottom line. So it's not behaving the way you expect it to behave without a controller. Okay, so let's look at this PZ map because we've been doing it. So pole zero map. So there are 3 eigenvalues for the open loop system. One at negative 100, one at negative 30. These are okay. We like these 2. This is what we don't like. So what is the job of the controller? The job of the controller is to do what? To displace, guys, to displace this to the left side of the imaginary axis. So you have a system that responds to a command the way you want it to respond. So the command says, I want H to remain 0 at all time. That's your command. You say, I want this mass to be in the middle of the coil. Stay in as close as possible to the middle of the coil, despite the fact that gravity is pulling it down. So the controller controls the voltage that is applied to the coil to make that happen. So that's the job of the controller. So where do you want to put the eigenvalues? The first thing is to see whether or not the system is controllable. Is it possible to displace the eigenvalues and put them anywhere we want? So what we need to do is to form the controllability matrix, which is made of B and A times B. Do you remember that? So this is the controllability matrix. So what mistake did I make? Absolutely. So this is a third order system. So I need to go to A squared times B as well. So it needs 3 columns. So this is the controllability matrix. I need to look at its determinant. Is it 0? It's not, which means the good news is that you can control it. So this is controllable. And of course, we can look at the step response of the system. Let's go ahead and look at step response of the system, which means if you give it a constant voltage, what will happen to the output, which is the displacement of the mass, and this is what will happen. So it will simply keep growing. This is 0.2 seconds, but if you go if you let this continue, for example, for 2 seconds, you can see how how much it will grow. So it basically drops. Okay, so then we can go ahead and use the place command of MATLAB to set the eigenvalues, the 3 eigenvalues, anywhere we want. But let's, for sake of argument, say we want to put the eigenvalues here. So we want to create a pair of complex conjugates, so there is oscillation, and then put one of the 3 eigenvalues far to the left. So the dominant eigenvalues would be these 2. So we can talk about a specific value of damping ratio and a specific value of natural frequency. So let's go ahead and say we want a closed loop EIG to be located at minus 10 plus 10 times J minus 10 times J and minus 50. So let's say we want the 3 to be located here. I forgot this semicolon, that's why I get an error. So these are the 3 eigenvalues that we want to have. Then the next step is to calculate the controller gain. So K is going to be place of A and B and closed loop EIG, the variable I used to determine the location of. Okay, so it tells me with these 3 controller gains, you can achieve these eigenvalues in the closed loop. Let's see if that really happens. So A closed loop is A minus B times K. Then the A matrix of the closed loop is A minus B times K. So this is A closed loop. Let's look at eigenvalues of A closed loop. And as you expect, they're located where we want them to be located. Minus 50, minus 10 plus 10J, minus 10, minus 10J. And let's look at the response of the system. So we are going to look at step response. Let's create the system closed loop as state space of A closed loop. The other matrices remain the same. A closed loop B, C, and D. This is our new system with the controller embedded. And then we can look at step response of sys closed loop. And here you go. Here you go. So this is now a stable system. Even though it oscillates, it is not growing just without bound. So it oscillates, but it finds a steady state value. Okay, can you calculate steady state value of y? What is steady state value of y? That's your challenge. Find steady state value of y. I'm not asking you to find the numerical value. I'm asking you to give me the equation that would give me steady state value of y. So what is steady state value of y? Knowing that x dot is ax plus bu and y is cx plus du. In steady state, what is equal to 0? In steady state, x dot is equal to 0, which means a x steady state is equal to minus b times u, right? And x steady state, therefore, is equal to minus a inverse times b times u, right? Okay. So what is y steady state then? Is minus c times a inverse times b times u. Do you agree? Did I miss any step? Yes or no? Okay. So with now our question is, with closed loop system where A is a closed loop, what is Y steady state? What is Y steady state? So let's try this. See if we get the response that we saw in this simulation. So Y steady state is equal to, what is it equal to? It's equal to minus C times A inverse times B. So it's going to be minus C times inverse of A, now closed loop, times B. And let's look at the, this is a step response. So U is equal to 1. So it's equivalent to not multiplying by anything. So what is Y steady state? According to our calculation, is negative 0.028. Does the simulation show the same thing? Yes? Okay. But this is not where we want Y to be. Right? Let's say we want the mass to just go up from the middle by 1 unit and stay there. So R is equal to 1. So how do we make Y to become equal to R? What do? You add a pre-filter, which is the gain that is multiplied by R. So let's go ahead and calculate um, KR. What was the equation for KR? It's right here. The equation for KR is right here. It's minus 1. Let me bring to your attention this very quickly. Look at the equation for KR. This is minus 1 over C times A closed loop inverse times B. Do you see that? Now look at this. Y steady state is minus C inverse of A closed loop times B. So essentially KR is 1 over this. KR is 1 over this. Look at this again one more time. KR, this guys, with a negative sign is Y steady state. So KR essentially is 1 over Y steady state. So if Y steady state is not equal to 1, you find the number that you need to multiply it by to make it equal to 1. That's all. So KR, therefore, KR is minus 1 over C times inverse of A closed loop times B. And so it's KR has to be a negative number. Mine is 37.714. So with a negative KR, you can get to 0 steady state error. So you can make Y go wherever you want it to go. And of course, you can choose another set of gains. So these are two different cases. So these are we chose the eigenvalues initially to be located here. You can change your mind, or if the requirement for the design changes and you want to locate these two elsewhere, it's possible because this system is controllable. It simply requires more control effort. It simply requires a larger voltage supply, for example. So if your controller calls for 10 volts, but your source of voltage maxes out at 5 volts, that controller is not going to be effective because your command calls for applying 10 volts to the circuit while your source of voltage is not sized up to that. So I'm going back to the point that I made a few classes before, that controller gain is not free. You can't simply go up in controller gain and assume it's just a number. It has real world meaning. In this case, for example, you have to have a larger circuit. A circuit that can take 5 volts is different than a circuit that can take 100 volts. So you have to basically beef up everything if you are going to go for a larger controller gain. So there is this implication. So this is the point that this last bullet is making. In general, the farther you make the poles to go to the left, you need more control effort, and more control effort means, of course, more cost. So this is the requirement. So you can make this system as fast as you want, but you have to pay for it. And this is just on the input side. We haven't yet answered the question that I posed in the middle of this class. How can I do full state feedback controller but do not buy a sensor for every state variable? In this case, if I want to implement the full state feedback controller, I need 3 sensors. One sensor to measure current, one sensor to measure displacement, and the last sensor to measure velocity. So I need 3 sensors to implement full state feedback controller. My desire is to just buy one sensor and simply measure output, which is the displacement. So I want to just buy one sensor, but still be able to put the eigenvalues of the closed loop anywhere I want, which is only possible with a full state feedback controller. So we still are dealing with that question. How can we do a full state feedback controller without spending on the cost of that extra sensor? I just want to bring to your attention that KR has another name. Sometimes it's called N bar, but it's the same thing. So it's a pre-filter. Sometimes it's called compensator. So bring to your attention that it's called pre-filter. Sometimes it's called compensator. Sometimes it's called N bar. So depending on which literature you read, so different names. So with that, we can go to steady state response that is desired. So the step response looks like this. Okay, so let's try to answer that question, and that was the reason we brought that block diagram up. So let's spend some time on this block diagram, because this block diagram, by the way, is the answer to my question. The question was, how can I simply and only measure y, but still have access to x? So I can implement a full state feedback control. Okay, so what do we have? Here is our physical system. So this shaded area is our physical system. This is the system that I want to control. So how are we trying to solve the problem? We are trying to solve the problem with a concept that is called an observer. So this is the solution that we came up with. What is the solution? Observer is a fancy name for the model. We have the physical system, true. That is the system that we want to control, but we also have a series of equations that constitute the model for this system. So we are going to take advantage of the model of the system. So in other words, what you see here is the physical system that we want to control, and we are only implementing one sensor to measure the output. The rest of what you see here is inside a computer. It's a program. It's an algorithm. So this is virtual. So everything that you see here is virtual, which means it's a program. It's in your computer. It's in your cell phone. It's in your embedded system. So what does this embedded system do? it receives the same input that the physical system receives. So this is U. This is the input that enters the physical system. So the same input that goes to the physical system, the same voltage that I apply to my magnetic levitation system, I take it and bring it to my computer, to my program. So what do I do with it? In my program, remember, we have a model for the system. So we do have a model for the system, which means I know matrix A, matrix B, matrix C, and D. These are known. So I have a model for the system, which means I know A, B, C, and D. So the same voltage that is applied, or the same input that is applied to the physical system, I'll bring it to my computer, and inside the computer, I multiply it by B. So this is now B times U. Can you see that? Okay. Then I'll bring A times X and add to it. So this becomes AX, so this line, so this was BU, then it becomes BU plus AX. And I'll put a little hat on X, and I'll explain in a second why we put a little hat on X. So far, this is BU plus AX. And what is BU plus AX equal to? According to the state space model, BU plus AX is equal to dot. It is equal to X dot. So this is equal to X dot. If I integrate X dot, everything again, by the way, guys, happens inside my computer. It's virtual. If I integrate X dot, what do I arrive at? I arrive at, so if you integrate, let me write it down again. If you integrate X dot hat, what do you arrive at? You arrive at X hat, right? Which you are going to use in a multiple way. The first thing is you bring it back in order to make BU plus AX. That's the first thing we do. The second thing is we multiply it by C, because C times X is equal to Y when D is equal to 0, which is in most cases. So Y hat, rather, is equal to C times X. Do you see what is happening here? What is happening in here is we are taking advantage of our model to predict a few things. One is our X vector. Remember I said I don't want to spend money to measure X, but I have an easy and cheap way to estimate X, to calculate X, to simulate X. And that is exactly what is happening in this computer program, which we call an observer. So far, what physical variable have I brought into this program? The only physical variable that I brought to this program is U, the input that goes to the system, right? Do you see that? The only physical variable that has entered my virtual program is U, the input to the system. So I have created an engine that estimates the state vector as well as the output for the system. Right? Now, how can I use this estimate of X? Here. What is happening here? We are getting estimate of X and multiplying it by the controller gain K, and use that to control the physical system. So the estimate that I have created virtually now exits the computer and enters the physical world. So instead of spending money measuring the real X, I'm just calculating X. I'm generating a bunch of numbers in a computer and use those numbers to control the system. Do you see what is happening here? I'm not spending on sensors anymore. Or if the variable is very far, it's not accessible, I don't have to travel 100 meters down the line and stick a sensor there. I'm just estimating it. I'm just predicting it. I'm predicting it so far only based on the input that I have plus the model that I have of the system. So what's wrong with that?
Accuracy.
Absolutely. I have a model that I think is the best model in the world, but we know all models are also wrong. It depends on how much details you have brought into your model, or how accurate you have measured the parameters of the system. For example, there is a resistance here. There is an inductance here. How accurate do you have those numbers? Would they not change over time? Of course they would. We know, for example, the value of resistance is sensitive to temperature. As you run this circuit and it gets hotter, the value of resistance changes. So how can I take care of those inaccuracies? Let's not forget something, guys. It is true that I'm cheap. I'm not spending on sensors, but I'm spending on one sensor. And that one sensor measures the output of the physical system. We said our limit is to spend only on one sensor. And that sensor is measuring the output of the system. Let's take advantage of it. So we have the physical system where we measure the output, and we have the virtual system where we estimate the output. Do you see that? So the physical system, this is measured. So this is measured. This is estimated. So let me differentiate between them better. So let me see if I can write this way, sideway. So this is measured. But this guy, y hat, is estimated. Do you see the difference? Now it should make more sense. Wherever we have hat, it's an indication that it's an estimate. It's virtually calculated. There is no measurement involved. Okay, so if these are dead on, if they're exactly on top of each other, our estimator is doing a fantastic job. It's predicting the output that is actually happening in the real world. But what if they are different, which in majority of cases, as we know, are going to be different because our model is not perfect. So what we are going to do is we are going to compare them, actually subtract our estimate from the measurement. Isn't that familiar? Doesn't that look like a feedback loop? It is actually a feedback loop. So we are going to take the difference between the two. Excuse me. We are going to take the difference between the two, multiply it by a vector of gain, and correct our estimate. See what is happening? This is L. This is the estimator gain. So this is L times y minus y hat. Y minus y hat is the error in estimation. How far is our estimation from the real world? So this line is error of estimation. Can you see that? The difference between output of the real system, the physical system, and the output of our computer program is the error in estimation. So I'm going to take advantage of that information and correct my estimation. How? I'm going to use it and add another input to the system. So the input to the system is not simply u, it is bu plus ax plus L times y minus y hat. So if the system is under predicting, I'm adding more virtual input to it so that the prediction grows. If the system is over predicting y, I'm going to subtract from it. So it's not a physical input that I put into my estimator, it's a virtual input. It's a correction term. That is, guys, called an observer, an estimator. And the same way that we design a full state feedback controller, we can design estimators. we can design an estimator that is much faster than the physical system. So if the physical system doing something, it is quickly calculating that what is happening in the physical system, so it doesn't lag behind. So we can actually make our virtual system faster than the physical system, which is a desirable characteristic. So you want your predictor to be faster than the physical system. So let's summarize. We have a physical system that we want to control. And we want to do full state feedback control because that's the best controller that we have arrived at so far. If the system is controllable, that means you can affect the response any way you want. You can put the eigenvalues anywhere you want on the complex plane, but we know that comes with a cost. With a cost that we have to measure every member of X. And if the system is of order 50, it means 50 sensors, which in most cases is not practical. We don't want to spend as much time and money to implement them, to maintain them, to make sure everything is calibrated and working at all times. Instead, what we are going to do is we are going to simply look at the input to the physical system and output from the physical system. We are going to bring these two variables into a virtual calculation machine. We call it an estimator or an observer. And I explained to you that we will, inside this machine, we implement our model, which is now in the form of a state space. And we are going to estimate X, which is useful for our calculation of the control input. We are going to estimate X. And we are going to continuously correct our estimation by comparing Y hat and Y, output of the virtual system and output of the actual system, and continuously correct our estimation. That is the basis of designing an observer. Okay? So the first thing that we want to introduce is the A matrix of the observer. Do you remember we talked about A matrix of the closed loop system? A matrix of the observer is this. A matrix of the observer is A minus L times C, where L is the gain of the observer, the gain vector of the observer. So by designing L values, by choosing L values, we can put the eigenvalues of the observer anywhere we want. So let's keep going forward. So we can use MATLAB, for example, and place command to put the eigenvalues of the observer anywhere we want. So we need to use the A matrix, the C matrix, and a vector of the eigenvalues where we want them to be. And that gives you the observer gain L. Now, is it possible to design an observer for every system? The answer is no. The same way, not every system was controllable, not every system is observable. So we have a test. You remember for controllability test, we had this matrix to check. A similar matrix exists for observability. This matrix is made of C. Let me remind you, the controllability matrix was made of B and powers of A. The observability matrix is made of C and powers of A. So C is row 1, CA is row 2, and we go all the way to 1 before the order of the system in powers of A. So it's very similar. So you can check the observability of a system. So in other words, if determinant of observability matrix is non-zero, if determinant of the observability matrix is non-zero, you can design an observer and put its eigenvalues anywhere you want on the complex plane. So you can make the observer do whatever you want. So, possible to design an observer with eigenvalues anywhere on complex plane. That's the meaning of a system being observable. So you can make an observer and create any dynamics in it that you want. That's the. So let's revisit this problem one more time. So we looked at this problem. This is the root locus with a proportional controller. We didn't really like this, so that's why we went to a full state feedback control. And I showed you that because this system was controllable, it was possible to put its eigenvalues anywhere on the complex plane that we wanted. And we looked at several examples where we put the eigenvalues anywhere we wanted using the full state feedback, which basically gave you closed loop A like that. Now we want to know if this system is observable or not. Why don't you please go ahead and calculate the observability of this system? And I'm going to bring the observability matrix up for you one more time. So this is the observability matrix. Go ahead and take 30 seconds and calculate the observability matrix. Is this system observable? In other words, can I design an observer for this system and put the eigenvalues of the observer anywhere on the complex that I want? So row 1 of the matrix is C. What is its row 2? Look at the formula one more time. Its row 2 is CA. And because it's a second order system, that's CA with power A of 1 is the highest power of A that we need to include in this matrix. So we need to have row 1 as C and row 2 as CA. So we already know what C is. Let's go ahead and calculate C times A. C is this row vector. A is this 2 by 2 matrix. So it's 1 by 2 multiplied by 2 by 2. So the result is 1 by 2. So let's multiply this row by the first column. What do you get? If you multiply that, you get 1, 0 multiplied by 0, 0. What do you get? You get 1 multiplied by 0 plus 0 multiplied by 0. The answer is, the result is 0. So row 1, column 1 is 0. Now let's go to row 1, column 2. 1 gets multiplied by 1. 0 multiplied by minus 3. So what is left is 1. So therefore, the observability matrix is going to be, in the first row, it's 1 and 0, which is C. And in the second one, you have 0 and 1. Now, the next step is to check determinant of this matrix. So determinant of the observability matrix is 1. And because it's non-zero, it means the system is observable. So we can design an observer for it to do anything we want it to do. So it's possible to put the eigenvalues of the observer anywhere on the complex plane that we want. So let's go ahead and design the observer. So our next step is, so we want to design an observer and we want to design an observer so that the poles of the observer are such that it is 3 times faster than the physical system. 3 times faster than the physical system. So let's look at the physical system. Physical system has 2 eigenvalues. The eigenvalues of physical system, so eigenvalues of, if you look at the root locus, it should be obvious that lambda 1 is 0 and lambda 2 is negative 3. Between these 2 eigenvalues of the open loop system, 0 is the one that defines the speed of the system. That's the dominant pole. That's the dominant pole. So let's say we want to design an observer where we put the 2 eigenvalues of the observer. So lambda 1 of the observer is at negative 3, and so is lambda 2 of the observer. So we are going to put the eigenvalues of the observer at negative 3. So it's a critically damped system with zeta omega n equal to negative 3. So omega n, natural frequency of 3, damping ratio of 1. So this is associated with the observer having a damping ratio of 1 and omega n of 3 radians per second. Okay? Are you okay with these calculations so far? If you're unsure, let me know and I'll explain more. Okay, so how can we bring the eigenvalues of the observer to this location? I mentioned to you that the A of observer, A matrix of the observer, is equal to A matrix of open loop minus L, which is the gain of the observer as a vector, times C. So A and C are known. If we have the model of the system, we know A and C. We are trying to find L, to put the eigenvalues where we want them to be. So design of an observer means designing L, or choosing values of L. So designing an observer means choosing values of L. Okay, are we ready to move forward? So we know already what the A matrix is 0, 1, 0, minus 3. So it is 0, 1, 0, minus 3. Okay. We also know what the C matrix is. C is 1 and 0. So C is 1 and 0. So what is L? We don't know what type of matrix L is. Can you tell me what type of matrix L is? It has to be 1 by 2. Why is that?
Because when you multiply it by the 2 by 1, it'll create a 2 by 2.
So shouldn't it then be?
I think I have that flipped. I know what
Yeah.
I'm trying to say. But
So the result has to be 2 by 2. We know that,
yes.
right? Okay. That's what it matters. So C is 2 by 1. Therefore, L should be multiplied by, L should be after C, not before C. And L has to be?
Shouldn't C be 1 by 2?
1 by 2, right? So it's 2 by 1 multiplied by 1 by 2 will give you a 2 by 2. So basically C should go first and L should go next. So if I can move this. So this is C. And L, we decided that L is going to be 1 by 2, meaning that I have L1, L2. Yes?
Shouldn't C be a row matrix, not a column?
Oh, I made a mistake. Absolutely. Okay. I take that back. Thank you. Yep. So absolutely, C is a row matrix. So let me rewrite it again. So C is 1 by 0, 1, 0. So this is 1 by 2. I apologize. So this is, this has to be 2 by 1 to make it happen. So L1, L2, so 2 by 1. Yeah, we got it. So designing an observer means finding values for L1 and L2 to deliver what we wanted to deliver. Okay, so let's go forward. And we need to calculate, of course, A of observer. So this becomes, this L times C becomes L1 here, 0 here, L2 here, 0 here. And we need to subtract this from the A matrix. So A of the observer is going to be equal to, so 0 gets subtracted from L1, so it becomes minus L1. 1 subtracted by 0, 0 subtracted by L2, so minus L2, and minus 3 is subtracted by 0. So this is the A matrix of the observer. So that's the A matrix. The next step is to find eigenvalues of the A matrix of the observer. So lambda I minus A of the observer. We need to find this and set it equal to 0 in order to find the eigenvalues of the observer. So this is going to be lambda plus L1 minus 1, L2 lambda plus 3. So this determinant would be lambda squared plus 3 plus L1 times lambda plus 3 L1 plus L2 equals 0. So we have done as we've done in the past, the way to find L1 and L2 is to realize that this should look like lambda squared plus 2 zeta omega n lambda plus omega n squared. And we have a desired value for omega n and a desired value for zeta. Zeta we want it to be 1, and omega n we want it to be 3. So that means we want this to be lambda squared plus 2 times 3, 6 lambda plus 9. That should give us the value for L1. So 3 plus L1 is 6. And 3 L1 plus L2 is 9. So that means L1 is equal to 3 and L2 is equal to. Now, is this expected that one of these two gains should be equal to 0? Why one of these two gains ended up being 0? The reason is right here. The open loop has had two eigenvalues, one at 0, the other one at -3. What we want to do is for the observer, we want the two eigenvalues of the observer to be both at -3, which means we're just trying to displace one of the two. So we don't need to put any effort to displace the other one. That's why L2 is 0. If you had chosen for the eigenvalues to be elsewhere, you would find non-zero L values. Okay, let's go ahead and use MATLAB to do the same thing. So let me clear memory. A was for us is 0, 1, 0, negative 3, 0, 1, 0, negative 3. This is the A matrix. The B matrix is minus 1, 4. This is the B matrix. C is 1, 0. And D is 0. So L is, and let's say observer eigenvalues, we want them to be located at negative 3, negative 3. So L is going to be place A transpose, C transpose, and observer again. I forgot a comma here. Says L1 is 3, L2 is 0. So if you wanted the eigenvalues to be located instead of minus 3 and minus 3, at minus 3 plus j and minus 3 minus j. Let's say for an odd reason we wanted the observer to oscillate. If that was the case, then the two controller gains would be 3 for L1, 1 for L2. So that's so let's look at another example. We've looked at this example many times. Let's revisit it. So we want to look at the example of the two-tank system and look at the observability issue. So remember U enters the first tank, and this in turn feeds the second tank. So H2, H1, C1, C2, A2, and A1. So the question is, if H1 is output or H2 is output, does it matter? Which one of these two systems is going to be observable? So why don't you give it a try?
You are the first person to join the conference.
Okay, so let's go ahead and bring up the A and B matrices. So if you recall, A matrix for this is minus C1 over A1, 0. C1 over A2 minus C2 over A2. This is the A matrix. And the B matrix is 0, 1. I'm sorry, it's the other way around. So it's 1 over A1, 0. Now, for the C matrix, we have two choices. If H1 is output, C1 would be 1, 0. If H2 is output, C2 is 0, 1. So the question is, would both of these systems be observable or just one is observable? So let's go ahead and set up the observability matrix. So This is again a second order system. So for this first system, so W observability 1, it would be 1, 0. And let's multiply C by A. So this row by this column, you get minus C1 over A1 and 0. And observability matrix 2, similarly, the C matrix is 0, 1. So here you have C1 over A2, and here you have minus C2 over A2. So which one of these two systems is observable? So let's look at WO1. Is the determinant 0? It is. So this is not observable. The determinant of this one is non-zero, so this is observable. Which means what? Which means if your output is the level of the first tank, if you're measuring the output, the level of the first tank, you're not able to estimate the level of the second tank. But if you're measuring the level of the second tank, you're able to estimate the level of the first tank because of the causality. Because the first tank causes change in the second tank, but change in second tank doesn't cause change in the first tank. So that's the reason that measuring H1 is not enough to be able to measure H2, but if you measure H2, is enough to estimate H1. So I'm going to stop here, and we'll continue next time.